In this lecture, we're going to look at the burglars problem. Okay, so assume that there's a thief, and the thief, every night the thief goes out stealing, and stealing, of course, at some point might generate some money, but there's also, of course, a possibility that the thief is caught, and then the thief supposedly loses all his money and also goes to jail. Okay, so the problem here with the thief is at some point, maybe he has sufficient enough of money such that he doesn't want to take the risk again to be caught, and he stops stealing and becomes a good person in society. Okay, so the problem of the thief is when to stop behaving badly. Okay, so let's assume that the capital that the thief has at a certain period is x, and we're going to assume that the thief has a utility function which depends on x, and it's given by 1 minus e to the power minus alpha x. Okay, so this last term here is decreasing in x, so because we have a minus sign in front, this will be increasing in x. Okay, and this is called the constant absolute risk aversion utility function, if you maybe have already heard of it, but it's a nice behaved, it's a concave, nice behaved utility function. Okay, so if the thief stops stealing, right, and becomes a good citizen, then of course he will have he can enjoy his money, and he will have a payoff of 1 minus e minus alpha x, and then everything stops. Okay, if the thief decides to continue on stealing, then, well, you have a discount rate beta, and there's a possibility, maybe without the discount rate beta, there's a possibility that he will be caught. Okay, if he gets caught, then he loses all of his money and he goes to jail. And assume that he gets caught with a probability p. Okay, so with probability p, he's caught and goes to jail. Okay, and with probability 1 minus p, well, he gains some money. Okay, and he goes on stealing for another day. Okay, so here we will have a continuation value because the game keeps on going, right? And we will call this v. So v is going to be my Bellman function. So you will have a continuation value of x, which is the capital that he has today, plus whatever he gains by going out stealing. Okay, and we call this g. Okay, so this is the gain when going out stealing. And here we're going to assume that g is random, right? So one night could be more profitable than another night. So we assume that g is random. In particular, g is distributed according to some distribution function p, which is distributed on R plus, right? So he always gains some money, but the return from stealing is something random. Okay, so we have to take the expected value tomorrow, right? So we're going to integrate this over R plus of PDG. Okay, so this is the expected value tomorrow, discounted by B, and this only occurs with probability 1 minus P that he doesn't get caught. Okay, so in order, so this is the payoff of continuing stealing. So this is a payoff of stopping, and of course the burglar is smart, so he's going to decide what to do. He's going to take the maximum of these two, and this is going to give him the value of x today. Okay, so this is the Bellman equation of the burglars problem. Okay, so I made a small mistake. So if he's caught, which occurs with probability p, then he goes to jail, right? And he loses all his money. So here we assume that the payoff is going to be equal to 0. Okay, so here we have p times 0. So this term will disappear, and we're only left with this term here. Okay, so we're going to assume some kind of decision rule, and then we're going to show indeed that this decision rule is the correct one. So we're going to assume that there's some amount of capital X star such that if X is bigger than X star, then he's going to stop. Okay, so he has enough money so that he's happy so he can retire. And if there's not enough money, then he's going to keep on taking the risk of going out stealing. So here he's going to continue. Okay, so we're looking for an X star below X star. If X is smaller than X star, he's going to continue robbing houses. If X is above X star, then he's going to stop. Okay, so first thing that we can do is we can try to determine X star, because at X star he's indifferent between continuing and stopping. Well, we know that this here at X star should be equal to this value at X star. Okay, so 1 minus e minus alpha X star is going to be equal to 1 minus p times beta, and then the integral of over r plus of v X star plus g of the probability. Okay, so if indeed I'm indifferent between continuing and stopping at X star, well, we know here v X star of g, X star plus g, well, this is bigger than X star. Okay, or at least as big as possible, greater or equal to X star. So here, whatever the value of X star plus g is always going to stop. Okay, so if this is indeed the decision rule, then we can already know what's the value here. Well, here the value is going to be equal to the first part here. Okay, because stopping is optimal, it's bigger than this one, so the maximum value is this one, so it's going to be 1 minus e minus alpha, and now it's X star plus g. Okay, so plugging this in, we have that 1 minus e minus alpha X star is equal to 1 minus p times beta, and then integrating over 1 minus e minus alpha X star plus g. Okay. So we can simplify a little bit this integral. So this is the integral of a difference. So it's the difference of the integrals, 1 minus p times beta. Then integrating this here over all amounts is going to give you 1. Okay, so this is just this factor. And then we have minus 1 minus p times beta. And then integrating over r plus of this here, e to the power minus alpha times X star plus g. And the exponent of a sum is equal to the product of the exponents. So we have e to the minus alpha X star times e to the minus alpha g p dg. Okay, so this is why this constant absolute risk aversion function is nice, because you can write the sum as a product of two terms. And here this first part doesn't depend on g. Okay, so you can put it outside of the integration. 1 minus p times beta, and then e minus alpha X star integrating over r plus of e minus alpha g times p. Okay, so far so good. So notice here that this term doesn't depend on X star, right? It's just a constant number. It's the expected value of something that only depends on g, not on x. So let me call this r. Then I have 1 minus e minus alpha X star is equal to 1 minus p times beta minus 1 minus p times r. Okay, that's this number here. And then times e minus alpha X star. Okay, so this is the payoff of stopping. This is the payoff of continuing at X star. They should be equal to each other. We can put this to the other side, put all the constant terms to the other side. So we have here 1 minus p times b is equal to e minus alpha X star. I have a 1 from this side, and then minus 1 minus p times r. Okay, This r here is smaller or equal to 1, right? Because then e to the minus something is going to be lower than 1, and then integrating over something lower than 1. So this is going to be lower than 1. So this here is greater or equal to 0. Well, if p is smaller than 1, this is strictly positive. Okay, and here this is decreasing in x. Okay. I forgot a beta. Right, so there should be a beta here, I think. Yes, sorry. So I hope it's correct now. So there's beta here. So this is decreasing in x. So there's a unique x for which this equality will hold. Okay. Which is going to give me this x star. So this already shows that x star is unique. There will only be one, because either this is below, and because this is a monotone function of x, this is fixed, so there's only one value of x star that satisfies this condition. Okay. So this gives me my x star. Well, basically what I can do, I can bring this to the other side. And I can take logs, and I can actually compute the value of x star explicitly here, but this is not overly interesting. So let me rewrite the condition here. So here I have 1 minus p times beta, and then on the other side I have 1 minus p times br. Okay, so this is lower than this one, and then e to the minus alpha x. Okay, and because this is decreasing in x, right? So for x bigger than x star, I will have that this here is lower, so I will have this. Okay, you can put the inequality here. So if x is bigger than x star, I would like to stop. Okay, and you will need this condition in order to show that it is indeed optimal to stop. Well, if x is smaller than x star, well, then I will have the reverse condition, right? This will be smaller than 1 minus p times beta r e minus alpha x, and I would like to show that this corresponds to the case where I'm going to continue. Okay, so this is going to be the remaining part of this lecture, is going to show indeed that under this case you're going to stop, and if this is true, then I'm going to continue. Okay, so let's first look at this here. So let's show that if x is bigger than x star, then I'm going to stop. Okay, so we're going to prove this as we proved for the previous lecture. So I'm going to define a set D is going to be a set of functions v, such that if x is greater or equal to x star, well, then I'm going to stop. Or in other words, v of x is going to be equal to 1 minus e minus alpha x. Okay, this is what I would like to show. Because if v of x is equal to the first part here, then stopping is optimal. Okay, so what I need to show is that for all v in the set here, because this set is closed, right, there's an equality here, t of v is also in D. So in other words, I need to show that for all x greater or equal to x star, t of v of x is equal to 1 minus e minus alpha x. Okay, so let's compute this here. So I have tv of x is equal to the maximum 1 minus e minus alpha x, and then 1 minus p times beta integrating over r plus of v x plus g p dg. Okay, so this is the Bellman operator. Bellman operator is like the Bellman equation, but instead of putting v here, you put the operator. So I know that v is in D. I know that x is bigger than x star, so x plus g is bigger than x star, right? Because you're adding a non-negative number here. So for x plus g, because v is in d, I know that this here is equal to 1 minus e minus alpha x. Okay, so plugging this in, I have that this is equal to the maximum of 1 minus e minus alpha x, and then 1 minus p beta r plus 1 minus e minus alpha x times the probability. And now I have something very similar as what I have before for x star, right? Here, except that now it's not x star but x, but I can make the same derivation, and I will find in the end that this is equal to the max of 1 minus e minus alpha x, and then 1 minus p beta, and then minus e minus alpha x, 1 minus p beta r. Okay, and then because of this condition here, you can rewrite this to show that, because basically this was derived from a comparison between this one and this one, and you can show that if this is the case, then the first component will be bigger. So here the maximum between this and this for x bigger than x star, right, is going to be equal to 1 minus e minus alpha x, and this shows this part of the proof. So for the second part of the proof, we're going to start from another set. The set is going to be, I'm also going to call it D. This is going to be the set of functions such that if x is bigger than x star, then I'm going to stop. And if x is smaller or equal to x star, then I'm going to assume that v of x is greater or equal to 1 minus e minus alpha x. Right? At least it's going to be better than to stop. And then I'm going to look at the set d tilde, going to be all the value functions v such that x is bigger than x star, then v of x is equal to 1 minus e minus alpha x. And if x is strictly smaller than x star, then v of x is strictly bigger than 1 minus e minus alpha x. So in other words, if x is smaller than x star, then v of x is strictly bigger than the payoff that I get when stopping. So this means that I'm going to continue, right? If this here is strictly bigger than the first component, then it should be equal to the second component, and the second component tells me to continue. Okay, so that's by this tells me to stop for every x smaller than x star. All right, so this is a closed set. I'm going to show that for all v and d, t of v is in d tilde. The first part is pretty easy because it's identical to what I have shown in the first part. Okay, so x bigger, greater or equal to x star, then v of x is equal to 1 minus e minus alpha x. This is identical. The second part, well, I have to show that t of v x is equal to 1 minus e to the power minus alpha x. For the second part, in order to show that tv is in d, I have to show that for x smaller than x star, well, tv of x is bigger than 1 minus e minus alpha x, and this is what I'm going to show now. Okay, so let's take x smaller than x star. Well, then tv of x is equal to the maximum of 1 minus e minus alpha x, and then I have 1 minus p beta integrating over r plus of v g plus x, or x plus g times p. Okay, so x is smaller than x star, so g plus x can be either smaller than or equal to x star, or smaller than x star, or greater or equal to x star. Okay, so if it's greater or equal to x star, well, then I know, or I already know because v is in d, that is equal to 1 minus e minus x applied here, right? So in other words, if it's greater or equal to x star, so g plus x is greater or equal to x star, then I know that vg plus x is equal to 1 minus e minus alpha x plus g. Okay, and if g plus x is smaller than x star, well, then it's in this category. So I know that vx plus g is greater or equal to 1 minus e to the power minus alpha x plus g. Okay, then it's bigger. So I know vg plus x is greater or equal to 1 minus e minus alpha x plus g, right? So in either case, it's bounded from above by this function here. So I know that this here is going to be greater or equal to the maximum of 1 minus e minus alpha x, and then 1 minus p beta, or plus 1 minus e minus alpha x plus g times p. Okay, because either g plus x is bigger and then it's equal, or g plus x is smaller than x star and then it's greater or equal. Okay, and then I can do the same derivation again as I did before. So the second part is 1 minus p beta minus 1 minus p beta times r times e to the minus alpha x. Okay, and then because x is smaller than x star, I have this inequality, right? And this inequality appeared from comparing this with this. And if this inequality holds, then you can show that the second one is bigger, right? So this one is strictly bigger than this one, so the maximum here will be bigger than 1 minus e minus alpha x. And this is what we needed to show. Okay, so this finishes the proof. So for our final exercise, let's go shopping. So we're going shopping and we're going to visit the store. We want to buy a gift, let's say. So if I visit the store, I can buy the gift, and let's say that I face a price P at the store, and I derive a utility U from purchasing the gift. Okay, there's no amount of gifts, there's only one item that I can buy. So if I buy at the price P, then I'm going to assume that I have the utility U minus P, right? So paying a higher price is costly, right? So this is my benefit, this is my cost, so I have U minus P. I can also decide not to buy the gift in this store. So I can continue shopping, and then I'm going to visit another store, and maybe I will see another price. Okay. So maybe I will see the price P tilde. Then I again have to decide whether to buy the good or not. But if I continue, there's also a cost, right? I have to wait for one period, that's the beta. And maybe I also have a search cost, so let me call this C. So this is a search cost because I spend some time looking for another shop where they might sell this good. Okay, so let's try to put this in a Bellman equation, this problem. So my value function will depend on the price P that I will see at the current shop. Okay, and I'm gonna have to decide whether to buy or to continue shopping. So it's going to be, as before, the maximum of two things. So the maximum of buying, which will give me utility U minus P. And then if I continue, and this is the more tricky part, well, I'm going to face a cost C. Okay, so this is minus beta times C. You can either assume that costs are discounted or not, it doesn't matter too much for the analysis. And then I'm going to find another shop after incurring the cost C. And then I'm going to have the value V of P tilde, right? And we're going to assume that I'm going to visit the shop at random, and so these prices are going to be random. maybe distributed according to some probability distribution P. And let's assume that P doesn't depend on this P here, right? So it's a random variable. This distribution doesn't depend on other things. So I'm going to have to integrate over P, and P can have a range, let's say R plus, right? Prices cannot be below 0. So this is my Bellman equation, so I can either buy and pay the price that I face now, or I can continue shopping, and it might be a benefit in continuing because maybe I will see a lower price, right? So it's going to be cheaper to purchase the goods later on. Okay. So one thing that's immediately obvious from this framework here, so this is the payoff of continuing, is that this value here doesn't depend on P, right? There's no P in here. This is because this is integrating over a random variable, the function V. This P here doesn't appear at this part here. So this is independent of P. So I can just give it a value. It's just a fixed number, right? So let me call this V tilde. Okay. So this here is decreasing in P, right? And this is a constant number, so there will be unique price at which buying and waiting give you the same payoff, right? So the price P, let me call this P star, at which you're indifferent between buying and continuing, is going to satisfy that U minus P star is equal to V tilde, where V tilde is just this fixed number here. So at P star, you're indifferent. If the price is below P star, then buying is going to be better than continuing. If the price is above P star, then you're going to continue, right? Because then this part here will be greater than this part. So we can use this a little bit to rearrange everything. So at P star, this is equal to this, right? So U minus P star is equal to minus beta C plus the integral over R plus of V P tilde PD P tilde. Okay, so let me write down the decision rule. If P is below P star, then I'm going to buy. If P is greater than P star, then I'm going to continue. Okay, so what's the trick I'm going to use now? Well, I'm going to, this is integrates from 0 to infinity, let's say. Okay, so here the bounds are 0, infinity. Well, I can write this as the integral of 0 to P star of V P tilde PDP, okay, plus the integral from P star to infinity of this. Okay, so this is just splitting up the integral into two parts. So this is equal to minus b to c plus, well, if the price is between 0 and P star, which is here for P tilde the case, right, then it's below P star, right? So here I'm going to buy, and if I'm going to buy, well, then I know that VP is equal to U minus P. Okay, it's the first thing here, so I can simply substitute this in here. So this is U minus P tilde of P VP tilde. Okay, if P is bigger than P star, then I'm going to continue, and if I'm continuing, well, what's my value? Well, my value is V tilde, okay, and V tilde is U minus P star. Okay, so here I can substitute U minus P star P dP tilde. And notice here that this is just a fixed number, right? So it doesn't depend on P star. So this basically is just a constant. If my price is too big, I'm going to continue shopping, so my value doesn't depend on the price that I face anymore. So rewriting this a little bit. Okay, so this is 0 to infinity of u minus p star minus 0 to p star of u minus p star. And this first one, because this is just a fixed number, this is, I can bring it outside, and I'm integrating over the entire interval of probability distribution, so this is u minus p star. Okay, so let me continue here. So I have u minus p star. U minus p star is equal to minus beta times c plus this here, plus 0 to p star of u minus p tilde p d p tilde plus u minus p star minus 0 to p star of u minus p star dp tilde. So here I have an integral from 0 to p star, here I have an integral from 0 to p star. So the difference between two integrals is equal to the integral of the difference. So I have that u minus p star is equal to minus beta c plus u minus p star plus 0 to p star, u minus p tilde minus u, so the u cancels out, plus p star. Okay, so it's p star minus p tilde p dp tilde. And I see that I forgot a few things. Well, first of all, I should have written a beta here, right? Because you're discounting. So there should be beta here, there should be beta here. So everything gets multiplied by beta. I have to discount all the way. Okay. So there's a beta here, and there's a beta in front here, and there's a beta in front here, and a beta in front here, right? So there's a beta for the payoffs of the next period. So this is u minus p star, this is u minus p star. So 1 minus the beta, so I have 1 minus beta p star. It's very convenient if you know where you have to end up, then you can spot the mistakes along the way. Is minus beta c plus beta, the integral from 0 to p star of p star minus p tilde p d p tilde. And I made another mistake. Well, this is 1 minus beta times u minus p star, of course. And I can write p star on one side. I can divide this by divide this by 1 minus beta if I bring it to the other side, and then I have u here. This becomes plus beta c over 1 minus b, and this becomes minus beta 1 minus beta 0 to p star of p star minus p tilde pdp. Okay, so one last step. P star is equal to u plus beta 1 minus beta, which is here and here. So we're going to have c minus 0 to p star minus p tilde p d p tilde. So this is p star. This is also called the reservation price, and this is the you can call this the reservation price equation, or the fundamental reservation price equation. So it's not a closed form solution for p star, because p star is also here and here. Okay, but at least it gives you the trade-offs between having a higher or lower reservation price. So first of all, the first part is the immediate benefit that you get when buying the good. Okay, so if the immediate benefit of buying the good is larger, then the reservation price will also increase. Second, you have a cost which adds positive into the reservation price, such that if the costs of continuing, this is the C that I had here, if the cost of continuing is larger, then the reservation price is going to increase, right? This also makes sense. If the cost is increasing, then the price at which you're indifferent between buying and continuing is going to increase. Okay, so you're going to buy in the larger region. Okay, the price can be higher. And then the second part here is basically the benefit of waiting. So this only integrates from 0 to P star, so P tilde is always below P star. Okay, and this measures the wedge between your reservation price and the price P tilde, and this then integrates over the probability of getting such a price. Okay, so if the price is much below P star, and if the probability of such a price is very high, then this will be a large number. Okay, so this is basically the benefit of a lower price. So if you have a larger probability of obtaining a lower price, then the reservation price will go down. Okay, which also makes sense. The price above which you're going to continue shopping is going to go down, so that you're going to remain shopping in a larger area or in a larger price range, right? If this occurs here. Okay, that's it for this lecture. Thank you for watching.